Well, hello, pre-calc friends. We are starting out today with a lesson on what is a function. Hopefully you know this isn't how we actually look in real life, but I would enjoy being an emoji. Like that would be a kind of fun way to proceed through the world. But I'm Mrs. Lemke, and I'm the person who is saying, let's go here when Mrs. Fry says, hey, we got plans? Our plans are to learn about what is a function. Yay! Let's get started. Mr. Covey, as usual, way off ahead of us with his rocket. All right, so a function is basically an idea, or so that idea could be like literally an idea, it could be an equation, it could be some kind of other rule, and it's something that takes an input and gives an output. That's a sort of half definition because there is a little bit of a catch. So let's say that we looked at these two ideas. So if we have B of P, now notice how I read that. I used the word of, not B parentheses P, not BP, right? I said the word of, that's important. So if I have a rule B of P that takes a person and as an input, so the person's an input, and then the output is the person's birthday. You can imagine how that would work, right? I take a particular person like, hey, when's your birthday? And they tell me, right? That's a function. I also could have the reverse kind of that, where I have P of B, which is where you take a birthday as an input, and the output is someone who has that birthday. So for instance, B of Mr. Covey means I want to know the birthday of Mr. Covey. Everyone does, and you get to find out today. See, aren't you glad you're here? So the birthday of Mr. Covey is March 22nd. Excellent. I could do the same thing with Mrs. Fry. The birthday of Mrs. Fry is October 13th. So I had an input, and it gave me an output. That seems really good. Seems very mathy, very concrete, specific. Now let's look at what happens with the quote-unquote reverse way, though. Okay, if I have P of March 22nd, sure, that would give me Mr. Covey. But there are other people who have that birthday too. He's not the only one. And the same thing would happen with October 13th, right? We would get the very formidable Mrs. Fry, but there are other people who have that birthday as well. So that brings us to what the part that made me say that this was sort of a half definition. A function takes inputs. Oh, wow, I missed writing a verb. Hey, okay, is a rule, I meant to say, is a rule that takes inputs and gives outputs. Now here's the caveat. But what? Each input, what do we want to say there? Right, this was the issue. We want an input to give a specific output. Okay, so that's the important characteristic of a function. So this is worded kind of in a specific way, even though I'm not always very good at the wording. But each input gives no more than one output. It doesn't mean that you have to have an output. You can have an input for a function that doesn't give any outputs at all, right? I might put something into a function and I'm like, does not compute, right? That's possible. But if I do get any outputs from the particular input, I only get one. I do not get multiple, okay? Some math words that you might want to have awareness about. Inputs, link that in your head with the idea of the word domain. Outputs, link that with the word range. These are words that you might have seen in the past. Typically our input or our domain, that sometimes is our X variable, and our output or our range, that's sometimes our Y variable, okay? So really though, input and output, that's a really good way to think of it. There are lots of ways to represent a function. You can represent a function with these little mapping bubbles. So we have here examples and counterexamples of each of these modalities. So in mapping notation, you can see that that first guy there is a function. You might get nervous. You might say, wait a second, I thought we had this special caveat, this special rule. And we do have that special rule, but it's not being violated here. The fact that you have two different inputs go to the same output, that is not a problem for a function. However, what is a problem is if I look over to this counter example, I have here the input of 0, and that input of 0 is giving me 1, but that input of 0 is also giving me 0. That's not a function. It is something you can have in math. We would call it the more general category of being a relation, right? There's a relationship, but it isn't a function relationship, okay? So write a little note to yourself out to the side here. How can you tell function versus not function if you're looking at mapping notation? I would say, this would be my way of saying it, and it doesn't have to be yours, that this kind of splitting is bad, right? That is not a function, right? In a table, remember I want to have each input go to at most one output. So my input here are the x's, my outputs are the f of x's, and I've got 1 going to 11, 2 going to 9, 3 going to 9, 4 going to 5. Wait, is this a problem? No, that's not a problem. That's just like what happens up above where -2 goes to 4 and +2 goes to 4. It's not a problem. Functions can do that. However, let's look at our not a function. What is the problem there? Right, this right in here. -1 as an input goes to 2 different outputs. So -1 goes to 2 outputs. Right there, that's my problem. All right, under ordered pairs. Ordered pairs are just where you have a number, comma, a number. So everything's legit here with our first example. But what is it that's the problem over in the second column? Well, third column, technically. 3 going to 4 and 3 going to 7. So make yourself a note here about what is problematic about that. We can't have the same input going to 2 outputs. Another way that you can look at a function or not a function is with a graph. And I bet that some of you remember this idea from your algebra class, and if not, that's okay. You're going to pick it up today. So the first guy is a function, because if you think about each of the different x values, right? So here's an x value. I don't know what number that is. Here's an x value. Here's an x value. And each of those x values has exactly 1 point across from it. 1 dot. Not 2, not 3, not 4, right? 1. That's good. Now, that is not the case in our second picture. In our second picture, I have this input. Let's say that maybe that's at -1. I don't know. The graph isn't labeled with numbers, but you get the gist. If I look across from that x value, you can see I have 1, 2, 3 different outputs, right? Those outputs would be matching up with some 3 different numbers on the y in the y direction, okay? So this kind of picture gives us the idea that we often refer to as the vertical line test. And what I get nervous about with the vertical line test is just that sometimes students like embrace it so hard that they know the test, but they don't really know why. And that's always a concern. Mathematicians love to know why. And if you know why things happen, really math is not hard. Okay? It's the memorizing of random things without any connection to rational, like the rationale behind it or the reasons behind it. That's what makes math hard. Because if you just try to memorize this epic book of lists and like lists of things you need to know, that makes math, that would be really hard. Really, really hard. Okay, so try to always know the reasons, and then math is straightforward. Okay, so here, the reason that we would be thinking about a vertical line test is because we're checking in an efficient way to see if each x has one y. So it's sort of like taking a line like this and you want to like think of dragging it across the shape and say, okay, at any particular place for x, am I just hitting the graph once or possibly not at all? Right? Hitting it not at all would be okay as well. But then when you come over here and you think about dragging that line across, it's like, oh, violation, 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 all the way across, like all the time, right? It only takes one violation to not pass the vertical line test. So we would say the first graph here passes the vertical line test. It is a function. The second graph does not pass the vertical line test. It is not a function. All right, so I've already been using function notation with you, whether you realized it or not from the very beginning. We write functions as a label with a notation about the input. So this f says, hey, I want to call my function f. And this x is denoting what the input variable is going to be. So like when we had b of p, that was saying, I'm going to call this the birthday function where people are my input, right? So it's helpful to name functions because you often will have questions that have multiple functions in them. And that's why we don't just use y for everything, right? Initially, like when you first learn algebra, it's always like, oh, well, let's just have y equals 2x plus 5. Let's have y equals x squared. Let's have y equals blah, blah, blah. And that's great, except if you have a problem that has all those equations in it together, it's like, which y do you mean, right? It's sort of like when I first started teaching, the names Melissa and Jessica were very popular among the 14 to 18-year-old set, right, in the 90s. And I had a class, not kidding, my first year teaching, that had 3 Melissas and 4 Jessicas. Like, what? Very confusing, right? So it would be very nice to have like distinct, unique names for things. And so sometimes in a problem that has temperature, I'll have function T. Or if I have a function that's about pressure, air pressure, I might have P for pressure, right? And that's helpful because then as I'm working the math, I can keep track of what these things mean. It's not a bunch of Jessicas and Melissas, just saying, okay? So we have this function notation that has a name that's a letter, and then in the parentheses we have the input. Well, maybe my input for the pressure has to do with time of day, so I have P of T. Or maybe my temperature has to do with the day of the week it is or something. I don't know, I'm just making this up. Okay, so you can denote even with another letter what your input is, okay? Most common, we have f of x or g of x or h of x. Those are like the kind of standard ones. But it is nice to also use labels that make sense. Now, for the rest of our lesson today, we have some problems. And so I'm going to have you do a lot of these problems on your own and then come back to the video and see how you did to check your work. Now, that's a standard thing for teachers to do in a video. I just want to point out, since we're earlier in the year, if you decide not to do that, think of what you're actually choosing. You're choosing to not take advantage of the practice that I'm giving you at a time when it doesn't even matter as far as points, your grade, anything. So this is like the low key, low investment practice. So when one of the pre-calc teachers says in a video, pause the video, try the problems, then start the video again and see if you got them right, I beg of you to please, please do that. Because otherwise, the first time that you're put on the spot might be a time that it's for a grade that goes in the grade book. I wouldn't want my first time trying something to be where I'm assessed. I would want the first time where I'm trying something to be where I'm just hanging out at my desk, trying stuff, and if I get it wrong, I'm the only one who has to know about that. I'm just saying, it seems reasonable to me. So I beg of you to please do pause, please actually try, and then please listen to explanations to see why you get things right or wrong. It's going to help you learn in the long run. okay? I don't care if you're listening to this at 1.5 speed, you know, good for you if you can catch on to my words that fast. But I do care a lot that you must actually try, okay? All right, speech over. We're going to do a couple together, and then, like I said, I'm going to have you pause and try. So the first bit you need to notice is that there actually are directions up here, okay? And number one is just asking you to linguistically explain what f of 3 means. F of 3 means that x is 3, the input is 3, and you're going to find the output that goes with it. And we have an opportunity for you to do exactly that down below. So f of 3 means plug in a 3 for the x and find the y. Question, which I did not finish doing. Okay, this is your problem set. Question 2 says find the x such that g of x equals 15. Now notice how the way that that's written is not the same as this. It's not saying plug in 15. It's saying find x such that g of x gives you 15. So 15 is the output. Okay, I did not do a very good job here of keeping things in the boxes. Okay, so find x such that that's true is solving this equation. Okay, so I'd like you to pick it up from there. Okay, you're going to finish out the problems in these cells. Some of the problems utilize this graph. Ooh, maybe we should talk about this graph. So notice that there are some things that are like little holes. Those are not points. It means that the graph has points, dots, absence of dot, points like that. Okay, there's one spot that is missing in the midst of all that. That's what that little circle means. Okay, so this whole thing all together is considered to be one function. It's made up of pieces. We would call it a piecewise function. This math logic. Okay, so we would like you to pause the video, work the rest of these problems. When you come back, I will go through the answers. Pause it. Okay, here are solutions for the problems that you worked by yourself, getting the practice. Question 5 uses the same idea as question 3. You just plug in a 5 and work it out. Question 7, I know I'm skipping around. Question 7, you plug in a 4 into function f, you plug in a 6 into function g, you work it out. So these two questions are a lot alike in terms of technique. 6 and 8 are more like question 4. You were told an output value and you need to solve for the input value. A place where I would anticipate some people maybe having a mistake is right here. If you have x squared equals 4 and just x equals 2, you forgot that -2 times -2 also equals 4. Okay, so you would have two solutions that yield the same output. So let's think about that for a quick second, given the rest of our lesson. If I have f of 2 giving me, actually it's not, I think that's confusing, hold on. If I have an input of 2 that gives me 9, and I have an input of -2 that also gives me 9, is that actually still a function? It is. That's the case that that's okay. You can have two different x's that give you the same y. It's the other way around that's a problem in terms of being a function. Okay, so for the last part, you were looking at this graph. Here are the solutions. Go ahead and pause the video if you think you want to look at this for a couple minutes. Okay, the ones I want to highlight are question 10, f of 2. If I go up from 2, I end up at that empty hole. So that's why I wrote does not exist as my answer there. f of -5, this one for number 13, also has a hole lined up with it, but also has a point lined up with it. So that output is my answer at 3. I also want to talk about what happens in number 16. Gosh, this middle column is tricky. Number 16, where f of x equals -5. So I want to go to -5 for my outputs and look along that level. And you can see that I have a point here. And I also have this whole section of graph here. We would call that an interval, that whole interval of graph. So you notice that on my interval, I have an open bracket at 4, open bracket at 4, and a closed bracket at 8, because 4 itself is not included, but 8 itself is. So square brackets show inclusion. I'm going to just hang out here for a second on this slide. That is the end of this video lesson. I hope you had fun. I had fun. It was okay, right? Pre-calc, it's going to be all right. Thanks.